Hey folks, and welcome to a new video. So in my last video, it was the announcement video for SystemsCheck.dev, which is my new programming puzzles website that I've been working on. It is live now. Check the link in the description. You can go and solve the first 5 puzzles, which are all published right now. So go check that out if you haven't. What I'm going to do in this video is I'm going to look at the mission 1, the first problem that we have in the set of 5. I'm going to talk through the problem a little bit, talk through some of my thought process around how I came up with it and what it means to me. And I'm going to talk through a really basic solution for part 1 and part 2 of it. And yeah, we're just going to have a little bit of fun. I'm going to talk about it. So that's it really. Let's jump straight in. So this is our first problem. It is mission 1. It is called Reactor Cell Safety Shutdown Analysis. It's a prosaic name. I think I started getting into the idea of having puns for names a little bit later on, but this is the first one. So it starts off with some flavor text. So this is the very first puzzle, so I kind of had to set the scene a little bit in terms of the story text. So you're 3 weeks serving on the Starship Orion as a cadet on its maiden voyage. You haven't messed anything up yet, which is always good. There's a few things in here. It's all just a bit of fun, really. But we come down here and we start to get your first actual mission. So your terminal blinks at you and you have an urgent request and you got to get to work. So the chief wants you to figure out a problem for him. So in the flavor text, we have that Fleet Command have decided that so the Starship Orion, a brand new ship, has a brand new reactor design inside it, and Fleet Command need to monitor its performance. So you have to send reports back to them of the performance of the ship, of the reactor. So as we get down a little bit further, we actually get into the actual text that defines the problem. So this is kind of where it starts, the real key. The ship's reactor is made up of discrete cells. Power drawn from the reactor can be balanced across the cells so that no one cell overheats to cause a critical failure. One of the new pieces of technology is a load balancing technology that routes the load between the cells to balance the power draw. This new technology can be flaky, however, and there's thankfully a safety system which can shut down and re-enable cells if anything bad happens. So the chief has attached the latest set of reactor cell safety shutdown logs.log. So basically this is your input. It is meant to be sort of a log file containing events. And that is your puzzle input. This is the sample of what it looks like. I have it here on my machine as well locally. So it contains columns, pretty simple. Each one is separated by a blank line. First contains t equals, which is representing a point in time that the log pertains. The next column is the ID, which represents the reactor cell that you're talking, that the log relates to. And then the next one is a status. So this tells you what has happened at this point in time. So what this line means, T0 #0 disabled, means that at T0, reactor cell 0 was set to the disabled status. And then obviously enabled means the opposite of that. So see here at T3, the reactor cell 0 was enabled. So that means that if we read these log lines out, from T equals 0 to T equals 3, reactor cell 0 was in a disabled state, and then it got re-enabled after that. And then that you can basically use that same logic to figure out what the status is of each of these reactor cells as you go down through these logs. We go on to say a little bit some clarity, which helps to shape the problem bounds a little bit more. So they say the logs were seemingly taken directly after a full reactor reboot, which were some of the updates for the load balancing software, blah, 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 blah. So basically we can assume that all reactor cells were operational before T equals 0. So from any point before that, all the reactor cells were enabled, and then from T equals 0, that's where the events start, and that's how we can count what the status of our reactor cells are from there on. So the first thing that the chief would like to know is, of all the cells that were disabled for any duration, what is the single longest duration that any cell was disabled for? So this means that as you go down through the list of cells, you can figure out enabled, disabled, enabled, disabled, and they'll sort of toggle on and off as you go down through it. You can figure out what those time spans were between an enabled and a disabled call. And as you go down through the log file and count all of those, one of them will come out with the largest number overall. And that is the answer that we want. So some key things to note in this is that all I've asked for is what is the single longest duration. I haven't asked for what cell it is, so the cell itself doesn't actually matter. It also doesn't matter if multiple cells were disabled for the same duration. That doesn't also matter. As long as it's the longest number, that's all we actually care about. So 2 cells could have been disabled for the same length of time, which happened to be the longest. I don't care about that. I just want to know what that longest duration was. Well, sorry, I don't want to know it. The chief wants to know it. Yeah, that's me. I'm the chief in this instance. And what else is in here? Oh yeah, so one last bit of clarifying information that's in your in the text is that the log file seems to end very abruptly, seemingly interrupted by another full reactor restart. The reactor can restart surprisingly quickly, so you assume that any disabled cell will be fully enabled on the next second. So that means that, say, in this instance here, where we look at the t=3 here, and we say that cell number 4 was disabled. Now, I have it here so that this happens to re-enable it, but if we were to delete that line, and then we go down here, so cell 4 was disabled. When we get down to here, what we assume, based on what that text means, is that at t=9, cell 4 would be re-enabled again. So basically, if you just count one more second, everything is now re-enabled, so you can count your periods back. Again, that is a little clarifying piece of information, which makes a difference because some of your inputs could end up with overflowing to the bottom, and they're not all re-enabled by the end. So that's the basic problem statement. And the question at the end is for your actual set of logs, what is the longest single duration for any cell that any cell was disabled for? So here's the sample. For the sample, it's pretty simple. I think I have it. Yeah, I have it specifically called out here. Cell 1 was disabled at t=1, and it was re-enabled at t=8. So we see here we've got t=1. It was disabled. Cell 1 doesn't get mentioned again until we're down here to t=8, where it was enabled, which means it was disabled for 7 seconds, making that the cell that was disabled for the longest period. So that's the answer for the sample. My actual answer down here for my actual input was 22,291. We can have a look at my actual input, which is here. Your input will look something similar to this. It's roughly around 1,000 lines long. It's plus or minus some amount. It's not always exactly 1,000 lines. It's in around that. And you can see that the timestamps go up to, 52,000 seconds or as such. And that's it. The whole thing goes down like this. And we have the same setup, all these different ones. And you'll notice the reactor numbers. There's some up here. I think they go up to about 50. I can't remember exactly what it's set to, but yeah, it's some range between 0 and 50, I think, is what all the IDs of the cells should be. All right, let's have a look at the code. Let's see how. So this isn't actually the solution code. I should say this isn't the actual solver code that my that SystemsCheck is running on the backend when you submit it. I decided I wouldn't quite show the exact thing that's going on there, but I wrote some very simple Ruby code to solve both parts of this. So this should give you an idea about, this can be solved relatively simply. This is only, 40 lines of code, a couple of print statements and some comments in there. So the actual logic that solves this is very, very small. Now this is Ruby, which tends to be quite terse. The actual solver that runs in production for this is written in Rust, and it's a good bit longer than this. Also has some edge case checking and all that sort of stuff in it too. This is just quite a simple kind of solution to runs here. So let's talk about how it works. I've bundled both of the solutions into this one file, so they'll just print here and here. So there's very little difference between them. We build a data structure in the first one that in the first loop that we do here, which isn't actually used, it's only used in the second part. So we'll just ignore that for the first solution. But then it is used in the second part to calculate this thing. So we'll just ignore what that's doing for now. Okay, what do we need to do? First thing we need to do, we think we need to go through the lines, and we probably need to build some sort of data set that tells us what we're doing, or we need to kind of build up a flow of what's happening as the events are coming through. So we can do that by iterating through each line of our input file. In my case, I start iterating through it. This is just a parsing logic, which splits out my timestamp, my ID, and my little state command for what's actually happening. I'm going to build up a hash map of nodes. So these are basically each node, and it'll have the status of what it is. So each node is going to contain the time that something happened to it. So this is, number 1, number 2, number 3. Each of those, each reactor cells, basically. Don't know why none of them nodes. They're the reactor cells. This is with the reactor cells. So first thing we do, we look and see if the state is disabled. So that is if the command or if the log line tells us that that cell is going to be disabled. What we do is we insert a new record into that map containing the time when it was disabled. If it's not disabled, then we do something different. So what we do is we check our longest time, which we're recording up here, set it to 0 at the start. We also record the timestamp t as 0 at the start. And we do this little calculation. So we figure out, okay, well, what is the current timestamp t? Is it, okay, this also predicates that it exists, that the node exists. Obviously, you could do some of this coercion in Ruby. It works a little bit easier. But if it's enabled, okay, there's another slight assumption in here, which I'm able to do because I know that this exists. If you have encountered a cell that says enabled, there was previously one that said disabled. So that is true of this input. It will always be that way. So that means that, say, for example, when you see here that we have this cell being enabled, it meant that there was a disabled before. And that's guaranteed by the generator. The generator knows this, that if it won't put in an enabled log unless there was a disabled previously. So because of that, I'm able to do this direct check here without hitting a null problem, because it will have existed. By the time this trips, which hits this else, which is an enabled, this will be true because it will have already found a disabled. So I can do that and it works. You can't necessarily do that in your solution because you might not. Well, you wouldn't know it did. You just know it now because I've told you, which is not necessarily a problem. It's fine. It's just a basic null check would solve your problem there, and you could just move on and do a slightly different branch in the logic. It doesn't really make a difference. So we can do that anyway, figure out if our longest time, then we know if this is true, that we have a new longest time that something was disabled for, so we can set that longest. And then this nodes, it should probably be called a little bit clearly, maybe like disabled cells is probably what it should be called instead of just nodes. So it's disabled cells, fine. So we want to delete it out of that set because this cell is no longer disabled, so we'll just delete it. This disabled at time is used for the second part, so we'll just ignore that for now. But basically what we do is we create another hash map up here, which just records the timestamp, and then we stick in a count of all the nodes that are disabled at that time. Use that later on, that's fine. Then we have to do one last thing, which is we have to do one more loop through each of the nodes once we've gone through the whole file, and that is basically to get our t+1 timestamp at the end, which is just to figure out what the status should be after everything has reset at the very end, which is fine. We just do that so that we can end up sweeping up anything that was disabled at the very end. We come to the end and then we can calculate the times and see, are any of those actually longer? If they are, we'll update this thing. If they're not, we can just ignore them. That's fine. And then at the very end, what we've decided, what is longest, we'll output at the very end. And that's that. That's pretty simple. I can run that code. If I run it for so that's for the sample, I get 7, which is the correct answer. 3 is the answer for part 2. We haven't talked through that yet. And then for my input, I get the same thing. Well, I get the correct answers, 2291. And that is my answer, 2291. All right, that's part 1. Let's look at part 2 then. So for part 2, you sent off your results. The chief says that you did it wrong and he wants something different. So what he actually wants is to figure out for what period of time was the reactor working at its overall lowest capacity. So what that means is that if you have multiple nodes that are disabled at the same time, they, will count, each one counts for reducing the capacity of the reactor pretty much. So at some point, you had the most amount of cells disabled at some point, whatever that was. It could be 10 cells disabled, or it could be 20, or it could be whatever. And we want to figure out for what period of time were the most amount of cells disabled. And it's that period is what we're interested in. Similar to the first part, it doesn't matter what cells were actually disabled or enabled. It just matters the number of them, which gives us one number that we're looking for, which is the minimum amount that were disabled. And then the amount of time is just the duration that all of them were disabled for. And again, say, just an example, I got a question on a YouTube comment on my last video of this, where someone had gone ahead and attempted this part 2 themselves. They had a question, it was like, well, what happens if in the same second a cell that was enabled gets disabled, and then a cell that was enabled, a cell that was disabled gets enabled, and a cell that was enabled gets disabled in the same second? Then your total, what happens then? And my answer was, well, it's actually the same amount, because the net value, when you sum it all together, will just be the same quantity, because one's been enabled, one's been disabled, so they just take each other's place essentially. So the overall capacity of the reactor is the same amount, even though 2 different cells have contributed. Because again, well, I don't explicitly state this, but it's each cell contributes the same amount of power basically, so it doesn't make any difference. It's just a count. So this is a little bit trickier to solve. It was just kind of fiddlier to think about. It's not actually that difficult. But in the example I have, you can see I call it out. So between t equals 3 and t equals 6, cells 1, 2, 3, and 4 were all disabled. This was the largest number of cells that were disabled at once, meaning that for t equals 6 minus t equals 3 equals 3 seconds, the reactor was operating at its lowest capacity overall. And so 3 is the answer there. And then for my input, it happens to be 223 is the answer. So we have a quick look at the code for this. This is just this second little loop down here. So what I've done is I've recorded this disabled at time. So for each timestamp in the records that we care about, I'm updating the amount of nodes that were basically disabled at that time, which I know because that's what I'm maintaining here is this list of nodes. So anytime I hit this, I can stick that value in, and I know that that will be the correct thing. You'll notice that we have this like t equals 3 multiple times here. So by the time I've read the last entry there, this number will be correct. So if you were to terminate this prematurely, you would actually see the wrong number in there, but it's because each one runs down the list. You can stick that in and it will always be correct at the end by the time you get there. So yeah, I maintain a list, so I know at each event timestamp I know how many were disabled. So what I can do here is I can find what the max value there was, so I know what the max disabled count was. Then I can go through all of those timestamps. I sort them here because if you iterate the keys of a hash, you're not guaranteed a specific ordering. So you can sort them here, so you can guarantee that you're going 0, 1, 2, 3, blah, blah, blah. I pull out the value as I iterate through, basically determine if the value is the same as the max value. And then I record a start time. So this start being -1 means that I'm at the very, very start of my list. So it kind of changes the semantics of what we're doing here a little bit. And I record the start. Otherwise, if this isn't the case, then basically I do this calculation. It looks a bit funky, but basically the whole point of this logic is basically just to calculate the window of how much time has passed. So we look at the value for the key, the time start that we recorded, and we check that it's not equal to -1. We figure out if it's bigger, and then we can assign the new key to the max value, and then we can reset the time start to -1 again, which puts us back at the start of a period that we're looking at. So basically what we're trying to find the window that we're in. You start, you come down, oh, that's the max disabled value. Well, okay, how long did it stay that way for? We move down. If it changed, if it doesn't change, if it changes, then you know that you need to recalculate that time span, reset the thing. If it didn't change, then you can check against its max, and then you can, recalculate the value each time. And then once you do that loop, the value for max at the end is that max loop value. There's definitely other ways you could do this. This is just, I actually was funny. I started writing these puzzles quite a while ago, and I kind of forgot how to solve this, which is funny because I have the code for it. I have the exact code that I used to do it. And when I went and wrote this example, I wrote this just on its own in isolation as I thought through the problem. So I kind of wrote it as if I was someone who was doing this puzzle for the first time. And obviously I knew some of the nuances, like I said, with this check up here, that I knew that would be a stable thing to do. But I kind of forgot how to do this part, so I just sort of made something up. And then when I went back and checked my actual solution solver code, it's different. So it doesn't use the exact same thing. It actually does it slightly differently, which is amusing to me, which is that even, people are all going to come up with different ways to solve these problems, which is something that I really love. And I love when you see different people's code for these types of problems, that there can be wildly different solutions to them. And that even myself, the person who wrote this and should have a built-in internal knowledge of exactly how this should work, has been able to write two different solutions for the same thing without specifically trying to, just naturally the way it occurred to me to do it at the time. I don't know if that says a lot about me as a programmer. Maybe it says that I'm not that good, that I just do things as they occurred to me at the time. Or maybe that's a good thing. I don't know. Who knows? But yeah, that's it. That is our part 2. And again, we can have a look at what we outputted up here. 7 and 3 were the answers for the sample, which are indeed the answers here. We've got 3 and we've got 7. And then for my inputs, they were 2291 and 223. And yeah, we've got 2291 and 223 as my answers. So that is it, really. That is all I wanted to do. That's all I want to show you. I just want to talk through this puzzle. I might do more of these. I might go through each one maybe as I do it. Maybe I'll leave them a little bit of time between each one so that these videos don't act as just a spoiler for how if there's any secrets about the implementations underneath that would help to solve the problems. I might do one of these every so often just to talk about it, but I thought for the first one it might be nice just to kind of set the scene a little bit, talk about my thinking about it and how this works. So I think that is it for this video. I hope you guys have enjoyed it. I hope you take your own stab at SystemsCheck in general. I hope you take your own stab at mission 1 and come up with some different solution. If you do, please share it with me. I'd love to see the different solutions. And yeah, that is it for this video. So I will see you all in the next one. Bye bye.